Hi everyone. In this part of the lecture on the closed loop systems analysis in the steady state domain, we will have a look at the rejection of the sensor noise or attenuation of the noise. If we assume that a constant n or noise could be observed when we have a sensor which has a bias. Okay, so let's say we have a temperature sensor which always indicates 1 degree centigrade more than it actually is. So there is a bias coming from our sensor. And then we can say that we have a kind of step input for the sensor noise. So what are we going to do? The controller will try to stabilize the system on a wrong value. So instead of saying that the actual temperature is 25, with the sensor we read 26, and therefore the controller will try to stabilize the system on 26. And then the actual temperature will increase. Yeah. Okay, so let's see what happens in terms of the transfer functions that we have for the error. If you remember, we have E equal to S of S times R minus S of S times D plus T of S times N. So N is the noise signal. And since our focus is on the attenuation of the noise, we set the others to 0. So E of S will be equal to T of S times N of S. And then if we say that N of T is step of T, then we can find the steady state error, limit of E of T as T goes towards infinity, following the formulation here. So limit of S times E of S, which gives us limit of S times T of S times N of S. You could see it over there. And then if we continue to simplify this limit, we will end up with limit of S going towards 0, L of S over 1 plus L of S. This will be the steady state error for us in the case of analyzing the sensor noise. And then if for L of S we consider the same assumptions that we had, meaning that all the terms will disappear apart from the integrators. Then as S goes towards 0, where K is equal to 0, because we have our signal, the noise that we have for the sensor in the form of a step function, then our limit will be simplified to this. Steady state error will be equal to L tilde over L tilde plus S to the power of H as H goes towards 0. And now we have one case where H is equal to 0. So the type of the system is 0. We have a type 0 system. In that case, the steady state error will be equal to L tilde over 1 plus L tilde. And if H is bigger than 1 for type 1 and type 2 and higher type systems, the steady state error will be equal to L tilde over L tilde, which is equal to 1. Okay, so this is in this kind of behavior of the system with respect to the sensor noise when the noise is in the form of a step function. For type 0 system, we have L tilde over 1 plus L tilde. For type 2 systems, type 1 systems, type 2 systems, and higher type systems, the steady state error is equal to 1 indeed. Now, if you want to reduce or minimize the steady state error, we can do it only for the type 0 systems. And for type 1 and type 2 systems, we don't have any control, let's say. Even in the case of type 0 system, if we want to reduce the steady state error, we need to decrease the value that we have for L tilde. On the other hand, if you remember, the steady state error for the reference signal for type 0 systems is in the form of 1 over 1 plus L tilde. So if we decrease L tilde, the steady state error in terms of the sensor noise will decrease, but at the same time, the steady state error for the reference signal will increase. So it's not a good idea to decrease the L tilde in that sense. And then for type 1 and type 2 systems, which have a, let's say, proper behavior in terms of the steady state error for the reference signal in the form of step. Over there, the steady state error for step is equal to 0, but now we have it equal to 1 and we cannot change anything. Okay, so having said that, it's also better to have an idea of how the system works from a practical point of view. What we want to do here is that we have a sensor which gives us a wrong measurement. And since we have a wrong measurement, what can we do? We can't do anything in terms of setting the output of the system to a correct value because we don't have the correct value. We get the wrong measurement. However, this kind of problem with the sensors where they have bias can't be dealt with properly with the control system, but in such cases it would be better to replace the sensor and use a, let's say, correctly working one. However, as we will see later, our control system can deal with high frequency noise, which is most of the time present. Okay, so when we talk about dealing with the sensor noise or attenuation of the sensor noise, we will mostly deal with the high frequency noise signals. And later we will see that these high frequency noise signals could be attenuated by our control system. So we will not deal with the low frequency noise signals such as step input. Okay, so having said that, now we can have a look at our example of the DC motor. Here we have the schematic for the system. We already have the GP transfer function for the process, which is in the form of this transfer function 0.01 over the denominator. And for this system, someone has designed a PID controller. So we have the PID controller here. Someone has designed it. We will learn later how to design it ourselves, but we have the transfer function for the controller. And the designer had in mind to satisfy some specifications for the closed loop system. And here you can see the list of the specifications. Bibo stability for the closed loop system. Steady state error for a constant reference equal to 0. So for a step reference, the steady state error should be equal to 0. Sensitivity to a change in the DC gain of GP should be smaller than 10%, and perfect rejection of the noise of the disturbance, torque disturbance, in the steady state, where we have HP as well. We can analyze the design control system using MATLAB. In order to check the Bibo stability of the closed loop system, here we have defined the transfer functions for GP, as you can see here. So GP is shown as 0.01 over the denominator. And then we have the GC in the form of a transfer function as well, s squared plus 100 s plus 200 over the denominator. And then the T, the transfer function for the closed loop system, is formed using this feedback function. So T is feedback of GP times GC, which is what we have in the forward pass, and 1, which is in what we have in the feedback pass. You can have a look at the details of the feedback command later, but over here we have the transfer function obtained for this closed loop system. In order to check whether the closed loop system is Bibo stable or not, we can plot the location of the poles and zeros of the closed loop system with this command. PZMap of T gives us this plot of the poles and zeros, and you can see that all of them are located in the left half plane. If you want, you can also have a closer look at the exact location of the poles of the system. And as you see here, all the 4 poles that we have for the closed loop system, they have negative real part. And this means that our closed loop system is Bibo stable. In order to check the steady state error for a constant reference and see whether it is equal to 0 or not, we have the model of the system simulated here in the MATLAB Simulink. You can see that we have the GC and the GP as the plant with the same transfer functions that we had. We have the feedback, let's say the closed loop system in the feedback form over here. And this is what we have for the disturbance. So to check the steady state error, we can set the disturbance to 0 for now. And we set the final value for the reference input equal to 1. And it will start at the time equal to 0. Okay. Now if I run this, we will see the response of the system, the step response of the system in the scope here, and over there we can see whether the steady state error is equal to 0 or not. Okay, here it's running. And now we can have a look at the graph that we have on the scope. And here we can see how the system behaves. So for now you can see two indeed blue and yellow graphs. I will explain the difference later. But for both cases, you can see here that the steady state value for the output is equal to 1. And as a result, the steady state error is equal to 0. So our closed loop system is bistable, and it has the steady state error equal to 0 for the constant reference input. Now we will check the sensitivity to a change in the DC gain of the GP and see whether it's smaller than 10% or not. In order to check the sensitivity to a change in the DC gain of the GP, I have constructed the same system in the lower part as you can see over here. But for the GP, you can see that we have the multiplication by 10 for the numerator of the transfer function. So basically the DC gain of the system of the plant is multiplied by 10. And then we should see how the steady state value, let's say, of the output will change. This is something that we already have seen. We had seen in the graph for the oscope that the final value for both cases that we have here is equal to 1. So there is no difference in terms of the final value that we get or steady state value that we get for the closed loop system. Even when the DC gain of the plant changes, it is multiplied by 10 over here. And this would mean that we have, for the current situation, the sensitivity, the steady state sensitivity for the system is equal to 0, which is indeed the ideal case. So let's have a look at the graph that we get from the scope again, and I will explain it again over there. Okay, so now here you can see that both the yellow and the blue graphs, one comes from the yellow one is indeed from the nominal case, and the blue one is where the DC gain of the plant is multiplied by 10. They have differences in terms of the transient response, but in the steady state, you can see that both of them have the exact value of 1. The steady state error is equal to 0. So the sensitivity, the steady state sensitivity for this system is equal to 0. Now we want to see how the disturbance will affect the behavior of the system in terms of its output or the response of the system. For that, we have their disturbance input over here. I'll assume that it starts at the time equal to 2 seconds with the final value of 1. So we will have the step unit step, let's say, input as the disturbance. And then now we are going to see whether it could be rejected in a perfect way or not. Okay, so let me set this to 10 as well. And then let's run it to see how the graphs that we have for the output of the system will be different. Okay, so here in this graph you can see it. You can see what happens. This is the time equal to 2 seconds where we have the disturbance affecting the behavior of the system. We have some transient response, but again, in the steady state mode, you can see that there is no effect of the disturbance. So the disturbance in the form of the step input is rejected in a perfect way. There's no effect of it in the steady state response of the system.